All of this translates into the following strategy. We start with our computational basis state X. So that's the state in which all our initial quantum bits are in these states here. And then we focus on the one bit in here that we will only need once, and this is this bit here. And so we take this quantum bit and transform it into another state. And the state that we transform it into is Z0. In there we will need to make use of all the other bits as well, because this state has this form here. So in here, we really just have a fractional part multiplied to 2 pi I, so this is always a fractional rotation, and so we need to account for all the bits. But these are then n operations. In the process, we have erased the memory of this bit, so we have replaced this state by this state down here, but this is fine because we will not need this bit anymore. And therefore we can turn to the second quantum bit, and this we are going to transform into the state Z1. This will require us to use this bit here and all the remaining ones, so until here. But not the first one, so this will require us n-1 operations. And then as we continue, we will only need 2 bits to produce the state Zn-2, namely these 2 bits here, and just a single bit to produce this state here, which can be written indeed in this particular form here. So this has a plus sign in front of the state 1 when x0 is equal to 0, and a minus sign in the other case. Right, so altogether this is just one more operation, and when we sum up all these operations we obtain n times n plus 1 divided by 2 operations, which is indeed of the order of n squared. So this is our strategy. We transform these quantum bits step by step in this hierarchical fashion, always erasing just the information that we will no longer need. But what we need now is to see how this can be implemented in a quantum circuit. To implement this in the quantum circuit, we just need 2 elements. And the first one is our Hadamard gate. We have seen many times what it does to the computational basis states, but to see what it does in this context, it is useful to look at this again and rewrite it in a suitable form. So we know that it brings the computational basis states into these superpositions. But this we can also rewrite in the following form for an arbitrary value xn equals to 0 or 1, namely as this phase vector here. And so this now puts a certain phase vector in front of the state 1, which corresponds to half of a rotation in the complex plane. And these are the largest rotations that we would ever need, because multiplying these by powers of 2 we obtain integers, and integer rotations we can always discard. The second element is a certain controlled operation with a gate that carries an index n, and I just write this index here so that our notation doesn't become too cluttered. But what the control quantum bit is here triggering on the target quantum bit is this single quantum bit operation with an index n that leaves the state 0 untouched, but puts a suitable phase vector again in front of the state 1. So for n equal to 1, this would be again half of a rotation, but for larger values of n, these are smaller rotations. And then we line all our initial quantum bits up here as our initial state. And aim to produce these final states on the other side. And what we do first is to apply a Hadamard gate to our very first quantum bit. So this brings it into one of these superpositions here, and afterwards we don't have direct access to this value of the bit anymore, but we will not need it anymore. So this will be fine. But this state Z0 also depends on all the other bits, which we will still need, and therefore we preserve them by using them as control quantum bits, but in a way so that they multiply the correct factors to the bit, this quantum bit here, so that it will end up in the state Z0. And here we start with the index 2, which amounts to a quarter rotation. And then we continue with all the other quantum bits until we come to this one here, for instance. And this will trigger this controlled operation with an index capital N minus 1. And here we get this operation with an index capital N. So that will be the smallest rotation that we would ever need. And by this we already have obtained this state Z0 here, so this is already fine. Next we apply a Hadamard gate to this quantum bit. This will now again transform this bit into another state, so we don't have any access to the value of x capital N minus 2 anymore, but we will not need it anymore. And what this Hadamard gate does is to put the correct phase factor in front of the state 1 as required for Z1. But there are again other contributions also coming from the other bits. And so we produce these additional contributions by conditional rotations applied and triggered by the other quantum bits until we come to this one here. And this will now carry out a conditional rotation in the complex plane with the index N minus 2. And this one will now do this with an index N minus 1. And there we then have our state Z1. So this we continue on all the bits, transforming them all into these states Zn until we come to this one here. So there we again apply a Hadamard gate and then a conditional rotation with the index 2 triggered by this last bit here. And this already brings this into the state Zn minus 2. And so we have just the last bit remaining, and to this we apply the Hadamard gate, and this brings it into the state Zn minus 1. So now we have brought our quantum system from this state into this state. And on the way we needed n times n plus 1 divided by 2 operations, of which n of them are Hadamard gates, and the remaining ones are these controlled operations that amount to certain rotations depending on the values of certain bits. So this is a circuit for the quantum Fourier transform in its most general form already. But to see how this works in detail, it is also worthwhile to look at one special case. And this is the case of a system with just 3 quantum bits. So let us look at this special case of 3 quantum bits. So quantum bits x2, x1 and x0. And what they really represent is now a state indexed by this integer here, just written in binary representation. And on the other side we want to have the quantum bits brought into the state Z0, Z1 and Z2. Let me first specify the circuit that achieves this. So here we have a Hadamard gate And then we have some controlled rotations, but they now take a very specific form. So I give them some very specific names. So here we have another Hadamard gate and another controlled gate. And down here we just have one more Hadamard gate. Now here I have introduced some very special names for these gates. R2 I denote as S, and this is as a matrix, this gate here. And R3 I denote as T, and as a matrix it is of this form here. Now these are just the standard names for these specific gates, and I had mentioned them briefly when we discussed single quantum bit gates in general. So there I mentioned that we will need these gates exactly once at one place, and this is this place here. Okay, so let us see what this quantum circuit is doing to our states. And we start with this state here, and first just look at the action of the Hadamard gate. But as we do so, we are going to develop our final result. So this Hadamard gate puts a factor in front of the state 1, and this factor depends on x2. And then we look at the action of this controlled gate, and this is going to put another factor of I in front of this. That's the same as e to the I pi over 2, so a quarter rotation. But this only appears when x1 is equal to 1 because this is a controlled gate, and so we can write this in the following form. And finally we have this gate here controlled by the last quantum bit, and this is going to place this factor in front, but only when x0 is equal to 1. And this factor is just like a phase up here with pi over 4, so we can write it in this way. And when we look at this expression here, then we see that this is related to this number here, which is our x, by dividing this by 4. And this is indeed exactly the way that this number x enters the definition of Z0. So this works out. Let us look at our second quantum bit. Well, this is unchanged as it passes through this controlled operation because it is the control quantum bit. And then it comes to the Hadamard gate, and there it is placed into this superposition. So very similar to what we had above, but now with this value of x1. And then we have this controlled operation, which now rotates by pi over 2, but only when x0 is equal to 1. So we have this expression here. And this already looks a little bit like x again. We obtain something which is related to x by adding to this 2x2. And we are allowed to do this because this just adds a multiple of 2 pi to this rotation angle in this exponent here. So this is then again related to x, but not by division by 4. Instead we now have a division by 2. And this is indeed how x appears in the definition of Z1. And finally we have the last quantum bit, first passing through controlled operations as the control quantum bit, leaving it unchanged. And then it comes to the Hadamard gate, where it is placed into this state here. And you can probably already see where this is going. So to this we can add 4x2 and 2x1. So just obtain x in front of the pi, and this is indeed the way that x enters the definition of Z2. So at the end we have transformed this state x into the state x tilde. So this is how this quantum Fourier transform works in this particular case of 3 quantum bits. And there we see very concretely how it exploits a certain hierarchical structure namely the way that these numbers x enter the definitions of these states z. And this then scales up to the case of many quantum bits in the way that we described when we discussed the general circuit. And because we invested so much time in understanding it, we will then be allowed to treat the quantum Fourier transform as a black box. So as one single unit that transforms our computational basis state x into this state x tilde. And for many quantum bits, this is then significantly more efficient than anything that we can do on a classical computer. But the question is what we want to achieve, and therefore we should now turn to applications. We will look at 4 specific applications and start with a very general one, which is known as phase estimation.